So in previous videos, we have talked about all these ideas, mutually exclusive, independent, what formulas we can use for and rules or rules if things are or aren't mutually exclusive or independent. All fine, but then the problem comes, we get to a real question, how do we apply these rules? So this is a video where I'll start to talk about applying these rules. First of all, let's just review briefly, again, what do these two terms mean? Mutually exclusive means there is absolutely no way that these two things can appear at the same time. There is a 0% probability of them showing up side by side. These are often used for things of the same category. So for example, if I pull a single card from a deck, pulling a heart and pulling a spade are mutually exclusive, because if I pull only one card, obviously it can only be one suit. It can't be two suits at once. Similarly, if I roll a single die once, the faces of the die are mutually exclusive. When I roll a die once, I can't possibly get more than one face showing. So those are examples of mutually exclusive events. Independent means that finding out the probability of one tells you absolutely nothing about the probability of the other. In other words, the result of one outcome has absolutely no influence whatsoever on the result of another. Now, a few considerations about these. First of all, the conditions of mutually exclusive and independent are not common with people situations. They're more common with dice, coins, cards, etc. What do I mean by that? Well, if you think of the categories into which we put people, we can categorize people by their religion, by their political party, by their race, by their gender, etc., etc., etc. These are big, messy categories. We can't really say that any one category is mutually exclusive with any other. We can't say that any one category is independent of any other. Categorizing people turns out to be a very messy business because there are always those exceptions. There's people that are odd combinations of things. They're this political party, but they happen to be that religion, that sort of thing. Just human beings are just very quirky, and there are always exceptions to patterns. And therefore, these nice, neat distinctions of mutually exclusive or independent, they're almost never true when we're talking about classifying people. They work much better when we're talking about very simple, inanimate objects. So again, dice, coins, cards, these are the types of scenarios where we're actually going to be using the ideas of mutually exclusive or independent. Another big idea just to keep in mind, whenever you see the words without replacement, processes that involve those words without replacement automatically are never independent. Well, what do I mean by that? Well, suppose we're choosing cards from a deck without replacement. Well, when I pick the first card, all right, then I can figure out the probability that that card is a certain suit or something like that. But then when I go to pick the second card, now instead of 52 cards, there are only 51 cards because one has been picked already and it hasn't been replaced. So now picking a card out of a deck of 51, that's going to be a different probability than picking a card out of a deck of 52. And in particular, what I pick on the first deck. For example, I want to know the probability of picking hearts. If I pick a heart on the first draw, well, that's going to change the probability of whether I pick a heart on the second draw. And so without replacement, the different draws are going to always have influence on one another, and therefore they're never going to be independent. So that's just a handy trick to remember. When you see the words without replacement, you're not going to be using any of the independence rules. Okay. Let's look at a hard problem. In a certain game, in phase 1, you flip one coin as many as 3 times. If you flip 3 tails, you lose. You automatically lose. As soon as you get your first head in phase 1, you advance to phase 2. In phase 2, you roll a 6-sided die once. If you roll a 6, you win. For any other roll, you lose. What is the probability of winning? Now, of course, if this were an actual test question, we'd have to have answer choices. We're just going to treat this as a calculation here. You may want to pause the video here and attempt this problem on your own just to get a sense of it. So this is my abbreviation scheme for the problem. In phase 1, we're going to have up to 3 coin tosses. If I toss tail, 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 I lose. As soon as I get the first head, either on the first toss or the second toss or the third toss, then I advance to phase 2. Phase 2 just consists of a single roll of one die. If I roll a 6, I win. If I roll anything else, I lose. So first of all, notice that we're working with coins and dice. Again, very simple things. Whatever I do with the coins is going to have absolutely no effect on what happens with the die. The die roll clearly is going to be independent of the coins. And what this means is that phase 1 is independent of phase 2. So probability of winning, this is the probability of phase 1. What we get is the advance to phase 2. That's how I'll abbreviate it. And in phase 2, we roll a 6. Okay? That is a scenario that will result in winning. And because the two phases are independent, we can multiply these. So phase 1 results in advancing to phase 2 times the result in phase 2 is roll of a 6. Well, one of those factors is very easy to figure out. When you roll one die, what's the probability of getting a 6? Well, that's a probability of 1/6. So that means if we could figure out the first one, the probability that phase 1 results in advancing to phase 2, we would just multiply this by 1/6. So in a way, we're kind of halfway done with the problem. Now let's go and look at phase 1 in a little more detail. Let's think about the outcomes here. If I flip ahead, then I advance. If I flip tail and then head, then I advance. If I flip tail, tail, head, then I advance. If I flip tail, 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 then that's no good. Then I'm out. And I want to figure out the probability of that, and a direct calculation of that would be a little bit tricky. Notice that those three cases would have 3 different probabilities because they involve a different number of tosses in each case. But notice that of the 4 possibilities, 3 of them are the thing that I want, and 1 of them is not the thing that I want. This is an ideal scenario for using the complement rule. So the probability of advancing on phase 1 is 1 minus the probability of losing. Of course, the probability of losing is the probability of flipping 3 tails in a row. Well, what's the probability of flipping 3 tails in a row? Well, tail, end tail, end tail, that would be 1/2 times 1/2 times 1/2, which is 1/8. And so the probability of advancing would be 1 minus 1/8, which is 7/8. That is the probability that in phase 1 we wind up advancing to phase 2. So that's our first factor here. So we get 7/8 times 1/6, and this turns out to be 7/48. And this is actually the probability of winning the game. Now this problem here is probably a notch or 2 harder than anything you're going to see on the test, but it demonstrates the basic principles, dividing the problem into stages, and at each point analyzing, are things independent, are things disjoint, and can we use the complement rule to simplify? All of these are strategies that will help you analyze probability questions.
In this lesson, we're going to look at some of the options we have when solving probability questions. Now, when we began studying probability, we first examined this formula and found that we could combine it with basic listing or counting techniques to solve many questions. Later, we added more sophisticated formulas to handle more complex questions. Generally speaking, all of these boil down to 2 options to consider when solving probability questions. You can apply the basic probability formula, or you can apply one or more of the following probability rules. Now all we need to do is decide which approach is the best for a given question. The good news is that most probability questions can be solved using more than one approach. The bad news is that some approaches can take a lot of time to apply. So whenever you encounter a probability question, you should be aware of the options you have and choose that which is the fastest. In choosing the fastest approach, you should know the strengths and limitations of each option. We'll examine that here. Now, in an earlier lesson, we examined the following question, where a coin is tossed 2 times, and we want to find the probability that at least one toss turns up heads. In that lesson, we solved the question in 2 different ways. In one solution, we used the complement as well as the OR probability formula for mutually exclusive events. In another solution, we used the OR probability formula for mutually exclusive events, as well as the AND probability formula for independent events. As you saw in those lessons, the solutions took considerable time to complete, and you may have been wondering whether there exists a better approach. Well, as you may have guessed, the 2 approaches taken weren't the best for that question. However, the purpose of that lesson was to examine a systematic way to rewrite questions in order to apply probability rules. In this lesson, our goal is to determine the best approach, and by best I mean the fastest. So we already used some probability rules to solve this question. What are some other options? Well, another option is applying the basic probability formula, and as you will see, this is the best approach. We want to find the probability that at least one toss is heads. So we need to find the total number of outcomes as well as the number of outcomes with at least one heads. To determine the number of outcomes, we can either list all of them or we can use some counting techniques. In this case, it's easiest to just list the outcomes since there are only 4 of them. There's heads on the first toss and heads on the second toss, heads on the first toss and tails on the second, heads then tails, and tails then tails. Now, before we apply the basic probability formula, we should recognize the core limitation of this formula. It requires that each outcome is equally likely. So let's confirm this. Since the likelihood that a tossed coin will turn up heads is equal to the likelihood that it will turn up tails, all of the outcomes here are equally likely. So we can apply this formula. As always, we'll begin with the denominator. There are 4 outcomes, so the denominator is 4. Next, the numerator. How many of the 4 outcomes are such that there is at least one heads? Well, there are 3 such outcomes, so the numerator is 3. So the probability is 3/4 that at least one toss turns up heads. As you can see, this is indeed the fastest approach. Now let's look at a different question. Here we are randomly selecting 2 people for a committee, and we want to find the probability that both selected people will be women. Let's examine our options. One option is to use the basic probability formula. We can use this because when selecting 2 people, the possible outcomes are equally likely. To apply the formula, we need to determine the total number of outcomes, in other words, the total number of 2-person committees that can be created, and we need to determine the number of outcomes where both selected people are women. Let's begin with the denominator. How can we determine the total number of 2-person committees that can be created? Well, one option is to list all of the different outcomes. So let's let the letters A to J represent the 10 people, where the letters A to D represent the 4 men, and the letters E to J the 6 women. Now let's list possible outcomes. As soon as we begin listing some outcomes, we should see that there might be too many to list, so we should probably abandon this approach. Another way that we can determine the total number of outcomes is to use counting techniques. Here we have 10 people, and we want to choose 2 of them to be on a committee. Since the order of the 2 selected people does not matter, this is a combination question. So we can select 2 people from 10 people in 10 choose 2 ways. Now the numerator. How many of the outcomes consist of 2 women? In other words, how many different 2-person committees can be created with 2 women? Well, there are 6 women, and we want to choose 2 of them to be on a committee. Once again, the order of the 2 selected women doesn't matter, so this is a combination question. We can select 2 women from 6 women in 6 choose 2 ways. When we evaluate the 2 combinations, we get 15 over 45, which simplifies to be 1/3. So the probability is 1/3 that the 2 selected people will both be women. Now in this instance, we used the basic probability formula and some counting techniques to solve the question. Are there any other approaches we could have taken? What about using one or more of the probability formulas? Let's see. We want to know the probability that both selected people will be women. So what must occur in order for both selected people to be women? Well, for this to happen, the first selected person must be a woman, and the second selected person must be a woman. Here we have an AND probability, so let's determine whether the two events are independent. To do this, we'll ask the question, does the occurrence of one event affect the probability of the other event? For example, if the first person selected is a woman, does this affect the probability of selecting a woman as the second person? The answer here is yes, so these two events are dependent, which means we'll use this formula. When we apply this formula, we get the following. Let's begin with this probability, the probability that the first person selected is a woman. Well, there are 10 people altogether, and 6 of them are women. So the probability that the first person selected is a woman is 6/10. Now for the next probability. What is the probability that the second person selected will be a woman, given that the first person selected is a woman? Well, let's assume that the first person selected is a woman. Let's say that it is this woman. This leaves us with 9 people for the next selection, and 5 of these 9 people are women. So if the first person selected is a woman, the probability is 5/9 that the second person selected is a woman. At this point, we can multiply the two fractions to get 1/3, so the probability is still 1/3 that the two selected people will both be women. So which of the two solutions is the best? It's hard to say. They both probably took the same amount of time to complete. The important point to recognize here is that we were able to solve this question using more than one approach, so keep this in mind whenever you encounter a probability question. In this lesson, we examine 2 primary approaches for tackling probability questions. They are using the basic probability formula and applying probability rules. If you use the basic probability formula, you must determine the number of outcomes. To do this, you can either list the outcomes or you can apply basic counting techniques.